The Gibbard-Satterthwaite theorem. It turns out that Arrow's theorem has devastating strategic implications. We will study the issue in the context of social choice functions, rather than social welfare functions as we have considered until now. Let us start by defining strategic manipulations. Definition 9.4. A social choice function f can be strategically manipulated by voter I if for some collections of preference 1, preference 2, and preference n in L, and some preference preference prime for I in L, we have that A is less than A prime in I's preference, where A is the output of little f of 1's preference, 2's preference, I's preference until n's preference, and A prime is the output of the same little social choice function f of 1's preference, 2's preference, I's prime preference, and n's preference. That is, voter I that prefers A prime to A can ensure that A prime gets socially chosen rather than A by strategically misrepresenting his preferences to be I's preference prime rather than I's preference. F is called incentive compatible if it cannot be manipulated. The following is a more combinatorial point of view of the same notion. Definition 9.5. The social choice function f is monotone if f of 1's preference, 2's preference until I's preference, and so on until n's preference equals to I, which is not equals to A prime, which is the output of f of 1's preference, 2's preference until I's preference prime, and I plus 1's preference until n's preference. Implies that A prime is less than A in I's preference, and A is less than A prime in I's preference prime. That is, if the social choice changed from A to A prime. When a single voter I changed his vote from I's preference to I's preference prime, then it must be because he switched his preference between A and A prime. Proposition 9.6. A social choice function is incentive compatible if and only if it is monotone. Proof: take 1's preference, 2's preference until I minus 1's preference, I plus 1's preference, and so on until n's preference out of the quantification. Now, logically, not monotone between I's preference and I's preference prime is equivalent to a voter with a preference can strategically manipulate f by declaring the preference prime, or a voter with preference prime can strategically manipulate f by declaring the preference back. The obvious example of an incentive-compatible social choice function over two alternatives is taking the majority vote between them. The main point of this section is, however, that when the number of alternatives is larger than 2, only trivial social choice functions are incentive-compatible. Definition 9.7. Voter I is a dictator in social choice function f if, for all 1's preference, 2's preference, and n's preference in L, for all b not equals to A is greater than B in I's preference, implies that the output of f of 1's preference, 2's preference until n's preference is equals to A. F is called a dictatorship if some I is a dictator in it. Theorem 9.8. Gibbard, Satterthwaite. If f Let f be an incentive-compatible social choice function onto A, where the size of A is greater than or equals to 3, then f is a dictatorship. Note the requirement that f is onto S, otherwise the bound on the size of A has no bite. To derive the theorem as a corollary of Arrow's theorem, we will construct a social welfare function f, capital F, from the social choice function, little f. The idea is that in order to decide whether A is less than B, we will move A and B to the top of all voters' preferences, and then see whether little f chooses A or B. Formally, definition 9.9, notation. Let S, which is a subset of A, and the preference is in L, denote by preference to the S the order obtained by moving all alternatives in S to the top in the preference. Formally, for A, B in S, A is preference to the SB if and only if A is less than B. For AB not in S, also A is preference S to the B if and only if A is less than B. But for A not in S and B in S, A is preference S to the B. The social wave function capital F that extends the social choice function little f is defined by capital F of 1's preference, 2's preference, until n's preference, and set up the output as just one preference, where A is less than B if and only if f of the preference 1 to the set AB and the preference 2 to the set of AB and so on until n's preference to the set AB equals to B. We first have to show that capital F is indeed a social welfare function, i.e. that it is anti-symmetric and transitive. Lemma 9.10. If f is an incentive-compatible social choice function onto A, then the extension f is a social welfare function. To conclude the proof of the theorem as a corollary of Arrow's, it then suffices to show Lemma 9.11. If little f is an incentive-compatible social choice function onto A, which is not a dictatorship, then the extension capital F satisfies unanimity and independence of irrelevant alternatives and is not a dictatorship. Proof of lemmas 9.10 and 9.11. We start with the general claim which holds under the conditions of F. Claim for any 1's preference, 2's preference, under n's preference, and any s, f of 1's preference to the s, 2's preference to the s, under n's preference to the s, is in S. Take some A in S, and since a little f is onto, for some 1's preference prime, 2's preference prime, and until n's preference prime, f the output of f of the input of 1's preference prime, 2's preference prime, until n's preference prime equals to A. Now, sequentially, for I equals to 1 to 3 until n, change i's preference prime to i's preference to the s. We claim that at no point during this sequence of changes will f output any outcome B not in S. At every stage, this is simply due to monotonicity, since B is less than A prime in i's preference to the S, for A prime in S being the previous outcome. This concludes the proof of the claim. We can now prove all properties needed for the two lemmas. Any symmetry is implied by the claim since f of 1's preference to the set AB, 2's preference to the set AB, and so on until n's preference to the set AB is in the set AB. Transitivity. Assume for a contradiction that A is less than B less than C less than A, where less than is the output of the capital function f. Function capital F of 1's preference, 2's preference until n's preference. Take S equals to the set ABC, and using the claim assume without loss of a generality that f of 1's preference to the s, 2's preference to the s, and so on until n's preference to the s equals to A. Sequentially changing i's preference to the s to i's preference to the set AB for each I, monotonicity of f implies that also f of 1's preference to the AB, 2's preference to the AB, and so on until n's preference to the AB equals to A, and thus A is greater than B. Unanimity. If for all I, B is less than A in i's preference, then i's preference to the set AB to the set A is equals to i's preference to the set AB, and thus by the claim that f of 1's preference to the AB, B's 2's preference to the AB, and so on until n's preference to the AB, the outcome of this little f is equals to A. Independence of irrelevant alternatives. If for all I, B is less than A in i's preference, if and only if B is less than A in i's preference prime, then f of 1's preference to the AB, 2's preference to the AB until n's preference to the AB is equals to f of 1's preference prime to the AB, 2's preference prime to the AB, and so on until n's preference prime to the AB, since when we sequentially for all I flip i's preference to the AB into i's preference to the prime of AB, the outcome does not change because of monotonicity and the claim. Non-dictatorship obvious. The Gibbard-Satterthwaite theorem seems to crush any hope of designing incentive-compatible social choice functions. The whole field of mechanism design attempts escaping from this impossibility results using various modifications in the model. The next section describes how the addition of money offers an escape route. Chapter 10 offers other escape routes that do not rely on money.